before we begin the session, do you have any questions from this week's lecture or previous week's tutorial? Yes. Yes. Please ask. Sorry, can you repeat yourself? Oh, okay. So that is, I guess, the flow between plates, right? Oh, the pipe flow. Yeah, yeah. So we will be doing, first we'll go through flow through infinite plates, and then we will move to flow between flow inside a pipe. Okay. So this week and also the next week. So you do not understand the derivation or the setup of the problem? Derivation. Okay, I will be actually doing the derivation for infinite plates today, and if you want, you can try out for pipe on your own, and then we'll do it for flow through a pipe in the next session. Okay. Anything from last week tutorial? I'll start presenting my screen. So you can see my screen, right? Yeah. So can one of you tell me what is Reynolds number? What is Reynolds number? So you must have obviously heard. Oh, you've not heard about Reynolds number? Yeah. You don't know the formula. Okay. Okay, fine. So long back, like almost more than a century back, there's this scientist Reynolds who performed this very interesting experiment. So what he did was he took a tube. So this tube you can see, and it is clear, so you can see the flow moving through this tube. Okay, it's like a glass tube, and here it is immersed in a tank, and there is a valve over here, so it's basically like a tap. So you open this valve and the flow moves through the tube and then comes out. Okay, and depending on how much you have opened the valve, that will create some pressure difference, and that will increase the velocity. So you can control the velocity of the flow through the tube using this valve. Okay, and now what he did was he injected a dye which is injected at just one point, right? So if I zoom in and if I look at the pipe, there is flow throughout the pipe, but what he did was he injected dye only at this location, and then he observed what is happening to this dye. So basically he's looking at the streak lines. Remember we studied what is the difference between streamlines, streak lines, and so on. So streak lines is nothing but the path that is traced by this one particle in time, right? So if you are looking at this particle and this point, and you are generating particles at this point again and again, so all those particles, let's say at time t1 you generated one particle, at t2 that particle has moved forward, and at t2 you have generated another particle over here, right? So if I join all these particles together, that gives me the streak line. Okay, so now he observed the streak lines of dye throughout this tube, and what he found is that if the valve is set such that there is very low velocity, okay, so this is low velocity, what he finds is that the dye moves in a single path in a straight line. Okay, there are no curls or anything. It just, if it generates here, it just moves along this line. But as he increases the velocity, so you increase the velocity, and what he observed is somewhere at some moderate velocity he starts seeing these curls. What are these curls? These are nothing but eddies. Okay, so initially the particles, these dye particles which were moving in a straight line, now they started deviating and they started forming these curls or these eddies. If you increase the velocity further, what you see is that the flow becomes very hazy and eddies of all sizes are being produced, right? So here there are big eddies as well and there are very small eddies as well, and as a result the flow becomes very hazy. The dye, it seems to have mixed throughout, but see, there is a very important difference. If I zoom into this location and I look at the dye, it's not like you see okay, so for example, if you had taken a tank and you have water and you mix dye and you stir it and you allow it to rest, then the clear water will all become blue, right? But that is not what was observed here. So the dye has not completely mixed, but it is trying to mix. Okay, so there are these eddies, very large eddies and very small eddies. Eddies of all sizes have been formed, and the dye is trying to mix throughout the flow. But this is very different from a stationary case where you have fluid in a tank and you have mixed a dye in it and the dye spreads throughout, and after some time the entire water is blue. So that is not the case over here. The case is there are many eddies which are trying to mix the dye. Okay, so this is called turbulent mixing, and what the dye shows, what the dye is able to highlight to you is that there are these vortices being formed and there are vortices of many length scales. So this is called the turbulent flow, and Reynolds for the first time showed that there is actually a transition from laminar to turbulent flows. And not only that, he did several experiments and then he characterized that this behavior, it depends on the velocity. Okay, it depends on the density of the fluid, the velocity of the fluid, and if you're performing this experiment in a pipe, there are two parameters of the pipe which are important. So what is that? So you can see that there is a diameter of this pipe, okay, and there is a certain length. Okay, so there is a certain length. So for the pipe, this length L and this diameter D are very important. In fact, it is this L by D ratio which determines how far from the entrance will the flow transition to, will it start transitioning to turbulence. Okay, so Reynolds established that there is actually a non-dimensional quantity, and he so let me write that non-dimensional quantity for you. So he showed that there is a non-dimensional number which depends on the density of the fluid, the velocity as in the average velocity. If I look at the flow over here, the fluid is going in this direction, flow over here, it is going in this direction. So we cannot say anything about the velocity at every location, but there is an average velocity. So despite all the turbulence, there is some average flow from left to right, right? So this is the average velocity. This is very important. Okay, and then he showed that this rho, V and D is some characteristic length, and then you have a parameter, viscosity parameter. So this is important, and this quantity is non-dimensional, and your transition to turbulence depends on this. Okay, and this is what we today know as Reynolds number. I'm sure you must have come across Reynolds number, and Reynolds experiment is the first and most well known experiment that established that there are these different regimes and they are very different qualitatively. So, laminar and turbulent flows exist, and then between laminar and turbulent flow, this is called the transition regime. Right? Any questions about this? Okay, so you can understand why we call this laminar flow, because if I injected the fluid, the dye at this location, it continued to move in that layer. If I injected over here, it will continue to move in that layer. So it's like the flow has layers that do not mix with each other. Okay, that's why it's called laminar. It's layer like flow. But in turbulent, there is a lot of mixing. Okay, so any estimate about when does this transition happen? So at what Reynolds number should I expect that transition to turbulence will happen? Actually, there's a very famous graph which shows that as you increase the Reynolds number, there is drag force is created, and they show that the drag force is quite high in the laminar regime. So there is a laminar regime, then there is a transition regime, then there is turbulent flow. So the drag force in fact is very high in the laminar regime, but it decreases in the turbulent regime. So there are different regimes, and Reynolds number is used to characterize this. So if you actually look at many textbooks, they'll tell you that Reynolds number less than 2300 is considered to be laminar, and or rather, sorry, so Reynolds number more than 2300 is considered to be turbulent, and Reynolds number less than 1000 is considered to be laminar, and anything in between is a transition from laminar to turbulent. Okay, but this is the case in most scenarios. So most scenarios, what do I mean? If you look at any real world system, if you consider any pipe or let's say a flute or an engine, so these are real world systems where there is roughness in the surfaces, right? And the transition to turbulence can occur very quickly, because when there are these walls and these walls are not smooth, what will happen very close to the walls, because there is some roughness in the surface, and this roughness is of the order of nanometers or much smaller length scale. These very small roughness attributes of the wall, they can introduce some friction at this level, and that will, so the flow which was moving straight will now be disturbed, and that will create small vortices, and eventually there will be transition to turbulence. Okay, and this we can observe for Reynolds number greater than 2300. But some experiments have been performed where they smoothen the pipe, the surface of the pipe, and the more smooth the pipe is made, the more delayed the transition to turbulence becomes. Right, so what do I mean by delayed? So let's say if I make a flow regime and Reynolds number, and I tell you that the transition from laminar to turbulence happens at some critical Reynolds number. This critical Reynolds number is usually 2300, but if I make the pipe very smooth, so for very smooth pipes, and these pipes have to be manufactured in a very special way. So what we find is that the transition from laminar to turbulent can occur at much higher Reynolds number. And what is unbelievable is that some people have established that even for Reynolds number 100 and 1000, which is a highly turbulent flow in real world, but under laboratory conditions, people have established that even for this very high Reynolds number, laminar flow can be maintained. Okay, so what does that tell you about transition to turbulence? With this story, what do you think is the most necessary aspect for transition to turbulence? Smoothness of solid boundary. But what is the smoothness of solid boundary doing? It is introducing some very minor fluctuations, right? Yeah, and those minor fluctuations, what happens for Reynolds number less than 1000? Let's go back to our Reynolds number. So when is Reynolds number low? If I keep density as same, velocity, average velocity, let's say it's same, and the diameter of the pipe is same. So in Reynolds experiment, what did he do? He changed the velocity, right? And okay. So in Reynolds experiment, what did he do? He changed the velocity. He kept increasing the velocity, and that increased the Reynolds number. Now imagine that I can keep the velocity same, density same, diameter of the pipe is same, but I can change the viscosity. What will happen is any random fluctuation that is created, that will die out because of the viscous effects, right? If you are changing viscosity, you are changing the fluid. But let us imagine that we can do this in a thought experiment. So if you change the viscosity and hence you change the Reynolds number, so let's say I am increasing the viscosity and I have some roughness in the pipe, that creates some random fluctuations. But because I have increased the viscosity, these random fluctuations, they will be smoothened out. Okay, because viscous forces dissipate the fluctuations. As a result, what happens? If there are no fluctuations, eddies will not be formed and the flow becomes laminar. Okay, so you can now understand that this, whatever Reynolds number we have obtained, it is reasonable to understand that for low Reynolds number, the viscous forces dissipate the fluctuations. But for more than 2300 Reynolds number, what happens? The fluctuations that are introduced by the boundaries, or see, fluctuations can be introduced in many ways, but usually it is because of the boundaries of the pipe. Whatever fluctuations are introduced, they are not dissipated by the viscous forces, and that is why we observe transition to turbulence. By making pipe smooth, what do? We reduce the probability that there are any fluctuations created in the flow, and that's how you can maintain laminar flow at very high Reynolds. Okay. Okay. Any questions till here? Any questions till here? Anyone? Okay, I guess not. So let us now look at the case where you have flow through a pipe or flow between infinite plates. Now you have some entrance, okay, there is some entrance, and beyond that you have a pipe. Okay, so firstly what happens is you are injecting in fluid, right? How are you injecting fluid? So usually we maintain some pressure difference. So let us say this is station 1 and this is station 2. So we maintain some pressure difference, P2 minus P1. Should it be positive or negative for the flow to move left to right? Negative. Yeah. So if P2 minus P1 is less than 0, we will see a flow from left to right. Now, what happens as soon as the flow enters? Now it encounters this uh, the boundaries of the pipe, right? So just at the entrance, if I have to make a velocity profile, and when I say velocity profile, what it means is how is the velocity changing in this direction. Okay, so I'm going to call this as my, yeah, I'm going to call this as some y direction. So how does the velocity change in the y direction? So just at the entrance, the velocity profile is like this. At all locations, same velocity. Okay. But we know that as you move past this length, the flow is going to interact with the pipe and there is going to be friction. And eventually, what do I expect? Very close to the wall, what should be the velocity of the flow? 0, right? Because of the no slip condition. Yeah, no slip and no penetration. So the flow cannot penetrate the pipe, so there is no flow in the y direction. And here there is so much friction that fluid should not be able to move, so there is a no slip condition. So there is no flow in the x direction, right? Okay, so the flow is almost 0 and it cannot abruptly change to something non-zero. So it will slowly, so at the edges it is 0 and then slowly the flow velocity will be increasing towards the center, right? So this is how we expect the velocity profile to be, and this is called the fully developed velocity profile. Now in between, of course, there can be different scenarios. So here there will be a non-zero velocity close to the boundary and some very high velocity here, and this is a transient flow, so there will be a lot of forces acting close to the boundary of the pipe, the wall of the pipe. Okay, so now the next question is, when can I assume that this fully developed profile has been established? So you started with a velocity profile where the flow is such that it's uniform, right? It's a uniform flow, and then you get a fully developed velocity profile through a pipe. So can I find out what is this length after which the fully developed profile will be seen? Okay, so this length is called the entrance length. Entrance length, that is, after the entrance, after how much length will the fully developed profile be established? Okay. And this entrance length also, so let us say that this pipe has a diameter d. Okay. So this entrance length, let me call it LE. LE depends on this diameter d. It is a function of the diameter d. And what else can it be a function of? Viscosity, okay, velocity, the initial velocity, and so on. Now what is interesting is that you don't need to worry about all these multiple parameters. This length is simply dependent on the Reynolds number, and the Reynolds number of course includes everything that you said, so density, average velocity, the diameter, and the viscosity. Sorry. Okay. And empirically it has been established that for laminar, so for example laminar flows, LE by D is actually approximately equal to 0.06 into the Reynolds number, and and similarly there are results for turbulent flow as well. But I think it's an empirical result, so I'll leave it at that. So I hope you understand what is an entrance length. Any questions till here? So now let us take an example which is very commonplace in engineering. Let's say we have a piston cylinder combination. So where do we see piston cylinders? Okay, so first of all, what is piston cylinder? So let's say I have this cylinder, and inside it I have a piston which can move in and out, right? So do you know where do we find these piston cylinder combinations? Engines, piston cylinder engines, right? Okay. So this is very common, and if we have such a setup and there is usually some fluid between them, we can approximate this as flow between plates, because see, this piston and cylinder, they almost fit in together and there is hardly any distance between them. So if I zoom in, it's like there is a upper plate and there is a lower plate, and the flow is basically moving between them. Okay, so this is an approximation, but it works very well because of the dimensions that we are dealing with. And there can be other applications as well where you actually have two plates and flow moving between them. Okay. Another example that I can think of is, so well, it's not flow between two layers, but you can approximate it like this. So if you look at the flow in ocean, now flow in ocean is very turbulent, but there are different layers in the ocean, and flow between two layers of the ocean can also be approximated as flow between infinite plates. Okay, so we'll be deriving the equations for the velocity profile for fully developed flows between plates, and pipes we will do it if time permits. So I want you to derive it along with me, and stop me anywhere you have questions. If it gets too mathematical, we can discuss what is happening. Already some of you have doubts, so stop me as and when we do the derivation. Okay, so let me start with this is what we have. We have two plates, and I'll label this as y equal to 0, and let's say that this length is a, the total distance between these two plates. So we have y and x in this direction. So the first thing we know about a fully developed velocity profile, what are the boundary conditions? At y equal to 0, u is equal to 0, also v is equal to 0, right? And at y equal to a, again u is equal to 0 and v is equal to 0. Okay. So u is equal to 0 because of no slip condition, and v is equal to 0 because of no penetration condition. Okay, so now let me consider a small element, okay, over here, and I'm going to draw a zoomed in version over here. Now, what are the forces acting on this fluid element that I have considered? Let's say at the center, at this whatever is the location x comma y, the pressure P x comma y is known, and there is some, of course, some shear stress acting on it, which is known to us as tau. So, what are the different forces that are acting on this fluid element? Surface forces and body forces. Yeah, so surface forces are pressure and shear stress, right? So let us say that this this length is dx and this length is dy. Of course, there's a dz, but we are just talking in 2 dimensions right now. So if I move from this center location, I move in this direction, that is dy by 2, right? So at this surface I have I'm going to write only the x direction forces, okay? So in the x direction I have the shear stress tau. What is it? Tau xy, tau xz, what is it? Acting on the y. So the normal to this is in the y direction, right? So it is called the y surface. So tau y, and acting in the x direction. So tau y x. Okay. So there is shear stress. Always, if you are confused, always what you should do, take that element, draw the normal, and this is the normal n cap, which is in y direction. The force itself is acting in the x direction. So it has to be tau y x. In this case, if the normal is like this, normal is in x direction and the force is, let's say, like this, so it will be in the y direction. So it will be tau xy. So this is how you should know how to write the shear stress. Okay. So now we have this tau ix, but tau ix was at the center. As you move up, there is an incremental change in the shear stress. So that incremental change, I can say, is plus some dou tau by dou y, because I have moved up in y. Okay, so and which tau? It was tau ix, and into the elemental change, which is dy by 2. Okay, because this change is just dy by 2. Is it clear how we wrote this shear stress? Now this is the stress and we have to write the force. So for a force, we will multiply it with dx, which is the length along this, into dz, right? So dz is into the plane. Similarly, over here we will have tau yx minus dou tau yx by dou y into dy by 2. Again multiply to dx and dz. What are the other surface forces that we should worry about? See, I'm not writing the shear stress here because the shear stress, maybe let me just draw. So the shear stress will be like this. Okay, but these shear stress are in the y direction. I want to write the equation only in the x direction. What is the other surface force? Pressure, right? So pressure on these surfaces will be in the y direction, so let's forget that. In the x direction we have pressure like this. So at the center, if it is P, if I go dx by 2 on this side, I can say it is P minus dou P by dou x dx by 2, and here it is P plus dou P by dou x dx by 2. This is pressure, so again to write the force I need to multiply it with the area. The area over here is dz is into the plane, and this length is dy, so we multiply with dy dz. Similarly over here we have to multiply with dy dz. Okay, now remember we are looking at fully developed velocity profile. So what can I say about the elemental force? If it was going back here, if we were somewhere between this starting point and this entrance length, if we were in this transient regime, then there are unbalanced forces on the elemental fluid, right? But when you have fully developed flow, fully developed means what? Now there is no transients and all the forces are well balanced and everything, right? So for every fluid element the forces should be balanced. So if I apply this condition, so for fully developed flow, forces are balanced. So now if I balance these forces in the x direction, what do I get? So you have P minus dou P by dou x dx by 2. This is in the positive x direction, but this force is in the negative x. So I'll subtract minus P plus dou P by dou x dx by 2. Right? And this was multiplied to dy dz. Plus, what are the other forces in the positive x direction? Is because of this shear stress. So I have tau yx plus dou tau yx by dou y dy by 2, okay, minus, so let me write this here, yeah, minus again tau yx minus dou tau yx by dou y dy by 2 multiplied to, so this entire term is multiplied to dx dz, and this is equal to 0. So from here, the first bracket, what do I get? Yeah, minus dou P by dou x into dx dy dz, right? And from here I get plus dou tau yx by dou y into dy dx dz. And this is true for any elemental fluid, right? So I could have chosen any dx dy dz. So this and this is non-zero, right? So I can just remove these terms, and what do I get? Dou P by dou x is equal to dou tau yx by dou y. this is our first equation. Any questions till here? Okay. So now, what did I want in the first place? I want to describe the velocity profile. So we know that this is how the velocity profile should look like. We can imagine this, but I want a mathematical form that describes this fully developed profile, right? So basically, I want the velocity u and v as a function of x and y. Okay. So now my question to you is, can you tell me u, is it a function of x and y, or only a function of x, or only a function of y? In a fully developed flow, yes. Yeah, so if we have a fully developed flow, what it means is the profile is not going to change even if I move downstream, right? So again, going back to this picture, I start from this profile and I end up at this profile. So while I am in between over here in this regime, my profile is changing with x. So here, in fact, u is changing in the y direction and also in the x direction. But once the profile has become fully developed, it will remain like that even if I move forward in x direction. Okay, so u should not be a function of x, and u is only a function of y for fully developed flow. Okay, and if that is the case, we can also say that shear stress, because see, if at any station the velocity profile is same, then the variation of the shear stress will also be only a function of y and not a function of x. Okay, so I can say now that your tau ix is also just function of y only. So instead of writing dou tau by dou y, I can write d tau by dy. Okay. So now my equation becomes dou p by dou x is equal to d tau by x by dy. Now comes the next assumption. So let us assume we have a Newtonian fluid. So what do we know about Newtonian fluid? Yes. Yeah, so the shear stress is proportional to the strain rate, and the strain rate is what? So we know tau by x is proportional to du by dy. So this we know for a Newtonian fluid, and in fact we also know that tau by x is equal to mu du by dy, where mu is the viscosity of the fluid. So now we can use this and put it back in our original equation, right? So what did we have? We had d by dy. So if I take d by dy of tau ix, that is nothing but mu d square u by dy square, right? Okay. Also what I can do is I can integrate this equation. So now dou p by dou x take dy over here, integral is equal to tau ix. Okay, so let me write it here like this. We have tau ix is equal to mu du by dy is equal to integral dou p by dou x dy. So what is this integral? Dou p by dou x, is it a function of x comma y, or only a function of x, or only a function of y? Only a function of y. Why? Okay, again, why? Why is it only a function of x? Yeah. Okay, let's imagine there was some pressure variation in y. Let's say first of all p. If p is x comma y, let's say there is a pressure variation in y direction. What will happen? The flow will move from the bottom plate to the top plate, or vice versa, right? Whenever there is pressure difference between 2 points, let's say this is P1 and P2, then the flow will move like this. So if there was any pressure difference in y direction, then there will be a flow in the y direction, but we are not assumed anything like that. In fact, we are talking about laminar or turbulent flows, even let's say laminar flows. We are only drawing a velocity profile such that at any location flow is in the x direction. We have never drawn any flow in the y direction. So I can say that pressure is not a function of y. So dou p by dou x is also not a function of y. Okay, and this integral we can simply write here dou p by dou x into y plus some constant c1. Okay. Now we are close to what we want. We want the variation of u. So we just have to integrate once more. So what is that? We have du. We have du, which is 1 by mu into this dou p by dou x y plus c1 into dy integral. Right? So let us first just integrate. We have u is equal to 1 by mu dou p by dou x. Y dy integral is pi square by 2 plus c1 by mu into y plus some another constant c2. Okay, so the first thing you notice is u goes like y square, which makes sense because, go back to the velocity profile that you've been drawing, this looks parabolic, isn't it? So the solution that we have obtained is intuitively correct. Okay, now what do I do with these c1 and c2? How do I eliminate these integration constants? Yes, applying the boundary condition. So we know that at y equal to 0, what do I have? u is equal to 0. So that gives me c2 is equal to 0. Right? And again, y is equal to a, I have u is equal to 0. So that gives me u is equal to 0 is equal to 1 by mu dou p by dou x a square by 2 plus c1 by mu into a. So from here we can derive what is c1. from here, first of all, we can eliminate mu, and C1 is nothing but dou p by dou x 1 by 2, yeah, minus a by 2. Is this right? Is this right? What happened? No, but there's also an a over here, and I divided it. Okay. Okay, so now u is equal to 1 by mu dou p by dou x y square by 2 plus 1 by mu minus a by 2 dou p by dou x into y. So I can write u is 1 by mu dou p by dou x, and let me take, so there is also a half over here, so 1 by 2, and let me take a square as a common factor. So here there is no a square, so what do I need to do? I'll say y by a whole square minus, now I have taken a square as common, but here there is only one a, so I get minus y by a. So just a fancy way of writing, but this becomes very useful because remember, a was what? A is the total distance between the two plates. So I have now normalized the y direction with this length scale. So we have only one length scale in the problem. Everything else is infinite. In the x direction infinite, and in the z direction also infinite. There's only one dimension that we have to worry about, which is in the y direction. So the characteristic length scale was a, and that's what I have used for normalizing over here. So this is our velocity profile. Any questions till here? So you can do a similar thing for flow through a pipe. Now what changes if I am considering a pipe? What will be the difference? So you have to follow the same procedure, and for a fully developed flow in a pipe, again balance the forces for some elemental fluid. But what will change? What is difference between a pipe and a flow between two infinite plates? Yes? There's no difference? Why do you, yeah, that's how you do that's the process. But why do you have to do this? Because, so what you said is we have to use cylindrical polar coordinates. Cylindrical polar coordinates are used because of the cylindrical geometry of the pipe. But the most important thing is, see, in a infinite plate, if you imagine what we are talking about, this is the plate which is infinite in this direction, infinite in this direction, and it is also infinite in this direction, and so on, infinite here. And similarly you have a bottom plate, right? So the flow is between them. But when you have a pipe, then it is infinite in this direction, fine, but there is a two-dimensional. So if I cut a section, then at any section there is a two-dimensional constraint, right? And it is only in the third dimension that you have infinite length. Whereas over here, the constraint is in one dimension and the infinite lengths are in two dimensions. So that is the difference. coordinates. So naturally you will have more friction over here because it's from all sides. Okay. And it becomes simple to deal with cylindrical polar coordinates, and in fact if this is the diameter and let's say you choose your r equal to 0 as the starting point, so at r equal to 0 and then you move outwards, that gives you the r coordinate, and you also have the theta cap coordinate, right? So you can now imagine how will the velocity profile look like. So you are moving into this direction, which is the z cap direction. So the velocity u, will it be a function of r theta z? So for by analogy, if there is any fully developed flow, it should not change in the z direction, right? So for fully developed flow, u is not a function of z. What about r and theta? It will be function of both r and theta. Why? Okay, it is a function of r, that we know, right? Because if I take any section at this location, I know that with radius the flow is going to look something like this, right? What about theta direction? It will be similar in all directions. So should u be a function of theta? So let me ask like this, is there any flow in this direction? In the azimuthal direction, there is no flow. Okay, so u should only be a function of r. And you will get a similar form of velocity even for flow through a pipe. Is this part clear? Yeah, is this part clear? Should I move forward? Okay, no response. Okay, so let us get back to the flow between infinite plates, and let us now discuss the other quantities that we know about the flow. So we have the velocity variation with the y direction. We can also write the expression for shear stress distribution. So shear stress distribution. And we're talking about infinite plates. So already we said over here that tau ix is also a function of y. It is not a function of x. And from Newtonian fluid conditions, we said tau ix is nothing but mu du by dy. So tau ix is equal to mu du by dy, which is mu d by dy of this expression, right? Or rather this expression. Okay, so just do this derivative and tell me what do you get. This mu and mu gets cancelled. Again, dou p by dou x is not a function of y, so I can take it out. D by dy of what is inside this big bracket, so that is 2y minus 1 by a. Okay, so this is the shear stress distribution, and what do you see from here? So you see that tau ix actually goes like y. So the shear stress increases linearly. So I'm talking about two infinite plates. As I move away from the boundary, the shear stress increases linearly. Okay. So if I have to draw the shear stress profile, it is 0 at the boundary, maximum at the center, and similarly from this side. So this is how the shear stress profile looks like. So we can also define volume flow rate. Okay. What is volume flow rate? Area into average velocity. Okay, yeah. Either we can take area into average velocity, or what we can do is, we have these plates, right? Let me take a dA element, and there is flow through this dA element, and then I integrate it throughout this section. Okay, so I can take the velocity at any xy location. We fix x, but velocity as a function of y. Dot dA, and integrate it over this surface. So we already know the velocity profile. Let me write it: a square by 2 mu dou p by dou x. We have y by a square minus y by a. What about dA? So this is, if I take some element here, small element dy, right? So this is small element dy, and the rest of the area is in z, right? So it is a dy dz element. Let's say the normal is in this direction. Velocity that we have written at y is also in this direction. Okay, so this is v of y. So the dot product is essentially going to contribute 1. So we have this expression into dy. Okay, and I'm going to consider dz integral as the width, and that width you can take as unity. Or we can say I'm going to define the volume flow rate per unit length. So this is volume flow rate per unit length in z cap. Okay. So we have to just integrate this. So from where to where should I integrate? What are the limits? 0 to a. Yeah. Okay. So just integrate and tell me what do you get. wait for you to do the integration. Yeah. Okay. A cube by 12 mu into, okay, um, is there any positive negative sign? Just check again. I think it should be negative. Yeah. Okay. Why should it be negative? It's a volume flow rate, right? So volume flow rate per unit length is minus a cube by 12 mu into dou p by dou x. Now remember when I asked you if there is this infinite plate and here you have a pressure P1 and here you have a pressure P2. P2 is less than P1. Yeah, so dou p by dou x is actually less than 0. Right, so this is less than 0, so you should have a negative sign so that the volume flow rate, which is always a positive quantity, it can be positive, right? Okay. So that's volume flow rate, and in fact you can also say that if you are controlling the flow, you have applied dou p by dou x is approximately delta p by L. So you have a certain length L across which you have applied this pressure difference, so delta p by L, and or negative of delta p by L is dou p by dou x, which is what you have applied, and then q by L becomes a cube by 12 mu delta p by L. Okay, so I'll leave the rest of the quantities to you. You can also find the average velocity, right? So how do you find the average velocity? You know the velocity profile. Yes. Upon integral dy, yeah. And you can instead see integral u dy is exactly what you did over here, so you can also just take this q by L by the integral of dy, which is a, right? So that gives you your average velocity. So you can do that very quickly. That is a square by 12 mu minus dou p by dou x. Okay. You can also find what is the point of maximum velocity, and as we know by intuition, the point of maximum velocity is where? Where is the velocity maximum in the velocity profile? Y is equal to a by 2. So you can find this, you can verify that this is indeed the case. So what you need to do is you need to just take du by dy equal to 0, because at the maxima the derivative is 0. Okay. So you can verify this. Okay. Yes. Yes. Did I say the opposite? Oh, so sorry. Yeah, I completely missed the minus sign, right? Okay. Yeah, thank you. So the shear stress should be 0 at the center. Okay. And as you move towards the infinite plates, the shear stress increases in the opposite. Yeah, this is wrong. Okay. Is this correct now? It has to be a linear profile. Yeah. Okay, so let us quickly do the questions for today's session. So we are going to consider a hydraulic system which contains a piston, right? So I've already told you before that this piston cylinder assembly, the flow between the piston and cylinder can be approximated as flow between two infinite plates, right? So we have some hydraulic fluid between the piston and the cylinder. There's a gauge pressure of 20 megapascal and the temperature is given. A control valve consists of a piston which is 25 in diameter, which is fitted into a cylinder with a mean radial clearance of 0.005 mm. So what is this clearance length? It is basically the length between the piston and the cylinder, which you can see over here is demarcated as A. So we have to find the leakage flow rate if the gauge pressure on the low pressure side of the piston is given to you. So what do we need to find? Leakage flow rate. Flow rate is basically the volume flow rate. Okay, so we have to find the leakage flow rate Q. Okay, so ideally we expect the fluid to stay here, but it is going to leak across these boundaries into this area where there is no piston. Okay, so what is this leakage flow rate? And what is given to us? What is the quantity that is given to us? Delta P is given to us, yes. And what is delta P? So there are two pressures. One is this 20 megapascal and this 1 megapascal, right? Yeah, so what is delta P now? Yes. So delta P is 20 minus 1 into 10 to the power 6 pascal. So that's in SI units, which is 19 into 10 to the power 6. Okay. And we can now use this equation that we just wrote down. Yeah, Q by L is A cube by 12 mu delta P by L. So volume flow rate per unit length in the Z direction. Okay, so this is A cube by 12 mu L into delta P. Okay, so now what is A? A was, remember, it is the distance between the infinite plates. So that distance is this, A equal to 0.005 mm. So that's 5 into 10 to the power minus 3 mm, which in meters is 5 into 10 to the power minus, one second, yes, 5 into 10 to the power minus 6 meters. Okay. Okay, what else do we need? Yeah, so what is this L in the Z direction? So what is the Z direction now? See, if this is the infinite plate, this is my infinite plate over here. So I can draw this is the Y direction, this is the X direction. The Z direction is into the plane, but remember, if you remember, this is the cylindrical geometry. So Z is all along the cylinder. Okay, so Z is actually this entire length. Okay, so this L is actually along the circumference. So what is L now? Pi d. And D is also given to us. So the control valve has a piston which has 25 mm in diameter. Okay, so that's pi d, and D is 25 into 10 to the power minus 3 meters. Okay, so now we have Q is equal to pi into 25 to 10 to the power minus 3 into a cube, which is 5 into 10 power minus 6 to the power 3 into delta p, which is 19 into 10 to the power 6 divided by 12 into, so what is this capital L? That is this length of the piston, 15 mm. So L is 15 into 10 power minus 3 meters. And what remains is mu, so that I will give you, which is known in the question. Yeah, so the specific gravity of oil is given as 0.92. Okay, so this is the only information given to us. So we have to find mu. So let me just write mu here for a while. Yeah, how do we find mu? Okay, sorry. So this is given, one second. So the information about the oil, mu is equal to 0.018 kg per meter second, and specific gravity is 0.92. Okay, yeah, so this is given to us. So now we can find what is Q. So please calculate and tell me your answer. Please plug in the value of mu and tell me what you get for the volume flow rate. all of you are doing the calculation. Yes, can you repeat? 5.57 into 10 to the power, oh, 5.75. Okay. 5.75 into 10 to the power minus 11 meter cube per second. Okay, so what is that? I can write this as almost 57 into 10 to the power minus 12 meter cube per second. So 1 mm cube is 10 to the power minus 9 meter cube. No, so this is not the right answer. Can you just check your calculations? So I think I just did the calculation quickly. What I am getting is this. So I get 57542 into 10 to the power minus 10 to the power minus 12. So that's 57.5 into 10 to the power minus, so I take 3 decimals, 9 meter cube per second. So that's 57.5 mm cube per second. So that is the answer. Okay, so just check your calculations. Okay, let's move on to the next question for today. So we have a sealed journal bearing which is formed from concentric cylinders. The inner and outer radii are given to you. The journal length is also given, and it turns at 2800 rpm. So the gap is filled with oil in laminar motion, and the velocity profile is linear across the gap. So this is also given to you. And the torque needed to turn the journal, the total torque force is given. So you have to calculate the viscosity of the oil. Now, what is different in this problem is you have two concentric cylinders. So let me draw two concentric cylinders, and the journal length, the journal is turning at 2800 rpm. Okay, so there is motion, and if I have to approximate this as infinite place, so again you have some very small length between the two concentric cylinders, and one of the plates is moving, which you can determine from this 2800 rpm, right? So first we have to deal with this movement of the plate. So let's imagine a flow where you have two plates, upper plate and the lower plate, and the upper plate is moving with some velocity, let's call it up. Okay, so now what changes? We derive the velocity profile. Remember, we derive the velocity profile over here. Yeah, this was the velocity profile. And then we use the boundary conditions at y equal to 0 and y equal to a. So this is going to change now. Okay, so let me take this. And paste. Okay, so now what are the boundary conditions? At y equal to 0, this is u equal to 0. So the velocity profile will be such that there is no flow here, but as you move away from this boundary, there is flow. Okay, so the velocity profile will be something like this. And at the upper plate, so at y equal to a, so y equal to 0, u is equal to 0. At y equal to a, what is u? The velocity of the plate. Okay, and you can put these conditions into this equation that we had derived, and you can determine what is C1 and C2. Now in this question, what is given to you? That this velocity profile, which I have drawn here, is in fact linear. So the velocity profile is linear. Okay, so do you know the formula for the shear stress in this case? This is derived in the lectures as well, so I'm not going to go through the derivation here. Yes, what is the velocity profile, or rather, since we have to calculate the calculate the viscosity, right? So we have to find the viscosity. So what should I do? I should consider the shear stress, because in the velocity you have u is a linear function of y. So that from here I can derive that tau, which is mu du by dy, will be, what can I say about the shear stress? Come on, this is simple. Okay, so if u is a linear function, the derivative of that with respect to y is going to be a constant, right? So this is going to be a constant, and I'll leave the derivation to you, but the formula here turns out to be tau is equal to mu u by r outer radii minus the inner radii. Now the outer radii and inner radii, they are nothing but this length a, right? So this is mu u by a. Now how do I determine u in this case? So u is, see, this inner cylinder, which is your journal, this is rotating. So if this is rotating, and you know the omega of rotation, you know the radii, we can find the velocity, right? So what is velocity? omega into r, the inner radii. Okay, so omega was 2800 rotations per minute into the inner radii, which is inner is 25 mm. Yeah. And what is A, which is outer minus inner? So A is RO minus RI is actually 1 mm. Okay, so this was given as 25 and 26 mm, so A is 1 mm. So you can convert this to SI units. 2800 into, so rotation is 2 pi, minutes is 60 seconds. Okay, so now this becomes radians per seconds into 25 into 10 to the power minus 3. So you can calculate and tell me what is U. So just for consistency, let me write this as UP. Okay, the UP is the velocity of the plate, UP. Do you have any questions about how did we write that tau is constant? Okay, if not, please tell me what is the value of UP. Okay, 7.3 meters per second. I'll trust your answer. Right now I don't have an answer. Okay. Now what is shear stress? Of course, one is mu UP by A. But how do I determine the stress? So what is given to us? The force, the torque that is needed is given to us. What is torque? Torque is force into length, radius here. Okay, so it is force into the radius. So here we have shear stress, and shear stress is nothing but force by area. So first of all, the force we know is, it is torque by the inner radius divided by area. So what area do we take? So this is the cylinder and there's a length to it, right? So the surface area of the inner cylinder is what we have to consider as the area. So what is that surface area? It is this circumference 2 pi r multiplied to the length. Okay. So this is 2 pi ri into length L. Okay, so now torque is given. Let me add a page over here. Yeah, so the torque is given to us, which is 0.2 Newton meter, 0.2 divided by 2 pi into Ri square, which is 25 into 10 to the power minus 3 the whole square, into length L. So what is the length? Yeah, the journal length is 100 mm. So that's 100 into 10 to the power minus 3. So please calculate and tell me what is the value of tau. 509 Newton per meter square. Okay. Yeah. Okay, and what did we have to find? Sorry, just again on this page. So we had to find the viscosity. So calculate the viscosity of oil. So we know tau is equal to this mu up by a. We have already calculated up. So mu is equal to tau a by ut. So this is 509. A was 1 mm, so 10 power minus 3 by up, which is 7.3. So what do you get as the value of mu? So that's Newton per meter square. Meter per second. So this is per second. So that's nothing but Pascal per second. Yes, what is the value of mu? Point 0.069. Yes, that is correct. Okay. Now the next question is, so consider a steady, fully developed laminar flow through a duct of radius r. At what local radius r, the axial velocity is equal to the average velocity. So we have not derived the velocity profile today for flow through a pipe. I have left it for you to do it on your own, but if you have any questions, we can address them in the next session. But since this is already done in the weekly lectures, I hope you know what is the velocity profile. So can you tell me the velocity profile for fully developed flow through a pipe? Yes, let us consider this as given. So we have a pipe. The maximum radius of course is capital R. And it is basically infinite in this axial direction. So u as a function of r. Do you know the expression? Okay, have you seen the derivation in the lectures? Say something. Say, if you don't remember, just say you don't remember. Don't remember. Okay, but you have seen the derivation in the lectures, right? Yeah, okay. So for now, let me give you the velocity profile. Okay, so u of r is nothing but capital R square by 4 mu into dp by dx into r square by capital R square minus 1. Okay, so you can see immediately this is of the form of what you had in the case of infinite plate, where you had this y by a whole square, right?